Alright, we're going to begin our study of calculus with some analytic geometry. So before we get into kind of the calculus proper material, we're going to spend some time studying the relationship between graphs, the behavior that we might see visually on a graph, and what it looks like algebraically. And we're going to begin with some basic definitions. First, the distance formula. So if I have 2 points in the plane, x1, y1, and x2, y2, the distance between those 2 points is given by this formula. And, you know, I try to minimize how many formulas I find myself needing to memorize. We're going to derive this formula for ourselves and see that, in fact, if I ever want to find the distance between 2 points, I can use that distance formula, or I could kind of sketch it out and use Pythagoras. So let's say our 2 points are here. Here's, say, x1, y1, and maybe up here there's x2, y2. So that I want to find the value of d, the distance between those 2 points. The way I'm going to accomplish that is by drawing some perpendiculars. So I'm going to draw the perpendicular, this horizontal line over. I'm going to draw this vertical line down. And when we do that, you can see that we've got this nice right triangle. And now what we're going to do is figure out, well, what are the distances between of these 2 legs of the right triangle. And in order to do that, the first thing we're going to do is figure out, well, what are the coordinates of this point in this bottom corner. Now the x-coordinate has to be the same as the x-coordinate directly above, so that x-coordinate is x2, and the y-coordinate has to be the same as the y-coordinate directly to its left, which is y1. Now that we have the coordinates of that point, we can find the lengths of these legs. So this vertical length, a vertical length is always the top y-coordinate minus the bottom y-coordinate. So that's y2 minus y1. This horizontal length along the bottom, horizontal lengths are always right x minus left x. So that is x2 minus x1. Now, Pythagoras says that d squared is equal to x2 minus x1 squared plus y2 minus y1 squared. And to solve for d, we take the square root on both sides. So d is the square root of x2 minus x1 squared plus y2 minus y1 squared, which is the formula that we see up here. We're being really careful here. It might be tempting to cancel out the radical with the squares, but of course we cannot split up a radical over addition. So that's as simple as the formula gets. So we're going to do an example. Let's find the distance between a couple of points here. We've got our points 3, -2, and -1, -5. And, you know, I'm going to use this formula, so the first thing I'm going to do is write it down. And then I need to pick one of these points to be my x1, y1, and one of the points to be my x2, y2. It really makes no difference. I'm just going to say that the first point is x1, y1, and the second point is x2, y2. But if you changed it around, you'll get the same answer in the end. And now we'll just plug in our coordinates. So x2 minus x1 is -1 minus 3 squared plus y2 minus y1, that's -5 minus a -2, that's +2 squared. So I've got -4 squared plus negative 3 squared inside the radical. That's 16 plus 9, which is 25. Square root of 25 is 5. So there's the distance. Our next definition is the slope of a line. Again, say I'm starting with the known coordinates of a couple of points, x1, y1, x2, y2, and we get the slope by using this formula, y2 minus y1 over x2 minus x1. It is rise over run. I misspell rise on purpose. I want to remind myself that it's the y's that go on top. So the slope just kind of gives you a sense of if it's rising or falling. A positive slope is rising as x moves from left to right. A negative slope is falling as x moves from left to right. And also how steep it is. So larger numbers for slopes correspond to steeper lines. Let's find the slope of the line that goes through these points. Again, I'm going to start just by writing out the formula. And then picking one of these points. I'll just pick the first one to be my x1, y1, and the second point will be my x2, y2. So y2 minus y1 is negative 7 minus a negative 5, so that's plus 5, over x2 minus x1 is negative 2 minus 3. This is negative 2 over negative 5, and then of course negative over negative is a positive, so this slope is a positive 2/5. So the slope is one way to measure whether a line is rising or falling, and how steep it is doing so. But we have another way to describe that, and is by using the inclination of a line. The inclination of a line is the angle that it makes basically with the positive x-axis, or really with any horizontal line. So for example, if I have, so here's my coordinate axes, here's a line. The inclination of this line is this angle right here. So I start at the positive x-axis and go counterclockwise till I meet the line. So there's a line with a positive slope. I could also take a look at a line that has negative slope. Oops. Its inclination, again, I'm just starting on the I'm starting on the x-axis. It doesn't have to be the positive x-axis, but you want to be to the right of the line on the x-axis, and then draw that angle up. So there's the inclination of that line. The inclination is always an angle between 0 and 180. If you go beyond 180, then the line kind of turns back to like a positive slope line. So now we have these two different ways to measure how a line rises or falls, with the slope and we have the inclination, and they are related by this equation here, m is equal to tan alpha. And I think it's fairly simple to see why that should be the case. I'm going to just draw a quick little illustration of that, and just for simplicity, I'm going to consider a line that goes through the origin, but this could be true for any line. So there's a line. It happens to have a positive slope, and we know its inclination is that angle there. Now it goes through this. If it goes through the origin, in this case this is the point 0, 0, and let's say it goes through this point x, y. If we drop down a perpendicular, right, the slope of this line is y over x, right? The rise over run is y over x. On the other hand, right, y is the length of this opposite side. X is the length of this adjacent side. And so using SOHCAHTOA, some right triangle trigonometry. In fact, the TOA part tells us that tan alpha is equal to y over x, and that is exactly the slope there. So this relationship between the slope and the inclination is not too hard to see why that equation is true. We're going to do a couple of examples here. We're going to find the slopes of the lines with the following inclinations, and that's just a direct application, right, of this equation. M is tan alpha. So they're telling us what alpha is, right? So 45 degrees is alpha. So M, the slope, is tangent of 45 degrees. You could use your calculator if you like. 45 degrees is a really convenient angle. Tangent happens to be equal to 1 at this point, positive 1. And so for part B, our angle is 110 degrees. So we're going to throw that into the calculator, and this is a less convenient angle, so I'm actually going to throw that in there. So about negative 2.75. Okay. So if we're given the inclination, we could just plug it into that equation to get the slope. What if I know the slope and I want to go the other way around? So if I know the slope, right, in this case, in part A, they're telling me that M is equal to 2. So that means that 2 is equal to tan of alpha, and I want alpha. So if I know the value of tan alpha, and I want the angle alpha that's inside, well, this is what the inverse tangent or arctan function is for. So alpha is arctan of 2. Now, depending on your experience with pre-calculus and what notation you've already been using, you may be used to writing this as tan with a little -1 superscript, like inverse tan. They mean the same thing. I use the arc notation more often than this other notation, just because I find that it's easy for people to confuse that with an exponent when it's not an exponent. So, alright, so there's a little tangent, pun intended. Let's find arctan of 2 on the calculator. So hit the second key, tan, to bring up the inverse tangent function. Arctan of 2 is 63.4 degrees. So with a positive slope, finding the inclination is nothing more than an application of the arctan function. For a negative slope, we have to be a little careful. If the slope is negative, you might have already made this observation, so we have this remark at the end. You might have already observed this, but for an acute angle, alpha, that will always correspond to a positive slope, and if alpha is obtuse, that corresponds to a negative slope. So obtuse meaning, more than, greater than 90 degrees. The thing about your calculator and the arctan function is that it will never give you a second quadrant angle. It's not going to give you an angle that's bigger than 90 degrees, ever. So we need to kind of have a way for it to give us that. And you might remember from your pre-calculus days, the way that I usually do this is to find a reference angle. And the reference angle is always a first quadrant angle, an acute angle. So our slope is negative 0.312. Something like that, right? And we want this angle, alpha. And what we're actually going to do first is find this angle, which I'll just call alpha ref for a reference angle. Note that alpha reference is a first quadrant angle, like it's a less than 90 degrees. It's an acute angle. So to find the reference angle, what I'm going to do is set up the equation that 0.312, positive 0.312, is tangent of alpha ref. So that means that our reference angle is arctan of 0.312. and that's 17.3 degrees. Okay, so if I know the reference angle and what I want is this angle alpha, you'll note that alpha and alpha reference are supplementary. They add up to 180. So alpha is 180 minus 17.3 degrees. I get 162.7 degrees. And there's the inclination of that line. So it took, you know, a little bit more work to find the inclination for a negative slope. Alright, so next we're going to talk about some parallel and perpendicular lines. Now parallel lines, there's not a whole lot to say about those. We know that two lines are parallel if they have the same slope. And if you have the same slope, then you have the same inclination. Two lines are perpendicular. The geometric definition of being perpendicular means they meet at 90 degrees. From what you've done with algebra, you might automatically be thinking, well, if two lines are perpendicular, then their slopes are opposite and reciprocal. And that's also true, but that's actually a result of this geometric definition of what it means to be perpendicular, and we're going to show that. Right? So we're going to take two lines that are perpendicular, and we're going to use as a definition a perpendicular to mean that they meet at a right angle here. And we are going to show that the slopes of these lines are opposite and reciprocal. So, in other words, we're going to show that M2 is negative 1 over M1, or equivalently, and this might be easier, that M1 times M2, their product is equal to negative 1. So I'm going to just label these lines. This line with a positive slope, I'm going to call that L1, and the line with a negative slope, I'll call that L2, and I'll say that M1 is the slope of L1, and M2 is the slope of L2. Okay, so first a bit of geometry. If you look at this, maybe you've already observed it, we kind of have a nice right triangle here if I include the x-axis as the bottom side. And if I take a look at this angle here, well, this angle has to be complementary to alpha 1, right? Because the two acute angles in a right triangle add up to 90 degrees. So this is 90 degrees minus alpha 1. And now this angle, 90 degrees minus alpha 1, is supplementary to alpha 2, right? Because it forms a straight line with alpha 2. So I'm going to just sort of write that relationship out here. So alpha 2 is 180 minus, and then this angle, 90 degrees minus alpha 1. I'm going to simplify this a little bit. Let's see, if I get rid of parentheses and subtract, that's 90 degrees plus alpha 1. Now I'm going to rearrange this in a way that might not seem obvious that we want to do, but what I'm going to do is subtract alpha 1 and subtract alpha 2 from both sides. And that gets us the equation negative alpha 1 is 90 degrees minus alpha 2. So here I have an equation that describes how alpha 1 and alpha 2 are related. And so the angle on the left, negative alpha 1, is equal to the angle on the right, 90 degrees minus alpha 2. And what I'm going to do now is I'm going to take tangent of both sides. So tan of negative alpha 1 is equal to tan of 90 degrees minus alpha 2. So now we're getting closer to being able to make a statement about slopes, because we've got the tangent function involved here. I'm going to use a couple of facts. They're facts that you've probably learned, maybe you've forgotten at this point, and that's fine. I'm going to remind you, tangent is what we call an odd function. And what that means is that if I have tangent of a negative angle, like negative theta, that's equal to negative tan of theta. That's not generally true for all trig functions. It's only true if the function is odd. It's because it has symmetry about what we say. We say it has symmetry about the origin. But kind of when you think about manipulating it, it means you can kind of pull out that negative sign. That's not really what's going on. It's more of a statement about the symmetry and the geometry of it. But this is what we're allowed to do when we're manipulating it. Sine is also an odd function. Cosine is not an odd function. So it's not something that you can generally do all the time. But tangent is an odd function. And so over here on the left side of this equation that we're working with, I've got tan of negative alpha 1. So that's equal to negative tan of alpha 1. Now on the other side, we've got tangent of 90 minus alpha 2. Now this is equal to cotan of alpha 2. And that's true because cofunctions agree on complements. So I can replace 90 minus alpha 2 with its complement, which is alpha 2. If I switch out tangent for its cofunction, which is cotangent. Now we're getting really quite close. I just flipped from tangent to cotangent, and now I'm going to go back to tangent, but not by using the complement. I'm going to use the fact that tangent and cotangent are reciprocal functions. So cotan of alpha 2 is 1 over tan of alpha 2. So now I have negative tan of alpha 1 is 1 over tan of alpha 2, and now I'm going to apply what I know about slopes and their relation to inclination. Negative tan of alpha 1 is negative m1, right? Tan of alpha 1 is the slope of L1. And tan of alpha 2 is the slope of line 2. So this is 1 over m2 on the other side. And now if I multiply both sides by negative m2, we get m1, m2 is equal to negative 1. And so the slopes are opposite and reciprocal, which we could see by showing that their product is negative 1. You could also, one could argue that we kind of see it right here too, and that's fine. We're just going to state our conclusion. All right, so this was a good exercise. I like to just take some time and draw these connections. We have these two different ideas between different ideas of what it means for lines to be perpendicular, and we're familiar with both the ideas. We know that perpendicular means that they meet at 90 degrees, and we've learned at some point that the slopes of perpendicular lines are opposite and reciprocal, but maybe we've never actually seen the argument about why perpendicular lines have slopes that are opposite and reciprocal. We're going to finish up this section with one more example. We're going to show that the line segments joining these points negative 5, 3, 6, 0, and 5, 5 form a right triangle, and then we're going to find its area. So we're doing two things. Now, when I'm starting off with the problem, and there's a couple of things to do. I maybe have some ideas about what I need to figure out. I'm going to find an area of a triangle, so I'm probably going to want some side lengths and things like that. But the one concrete thing they've given me is the coordinates of these points. So I'm going to start by just plotting these points and seeing where I can go from there. So one point A is negative 5, 3. Point B is 6, 0. And point C is 5, 5. So I'm looking at the triangle. Formed by connecting these points. Now, I want to show that it forms a right triangle, and, so that means I just need to show that two of these lines are perpendicular. And without plotting the points, I could just sort of go and find out all these different slopes. But since I plotted them, I'm like really quite sure it's going to end up being this angle right here at point C that is perpendicular. That's the right angle. So I'm going to just find the slope of AC and the slope of BC and show that they are opposite and reciprocal to each other. So the slope of AC, let's see, I'll treat point C like it's my x2, y2 point, and point A is x1, y1. So let's see, rise over run, that'll be 5 minus 3 on top, divided by 5 minus negative 5, so that's 5 plus 5. That's 2 over 10, or 1/5. So that's the slope of AC. The slope of BC, again I'm going to treat point C like it's my x2, y2. So that will look like rise over run. Rise is 5 minus 0 over 5 minus 6. And that's 5 over negative 1, or negative 5. And these are opposite and reciprocal. Which means that we do in fact have a right triangle. So that's the first thing they've asked us to do. And then they say, then find its area. Now, because we have a right triangle, that means that we have two perpendicular lines. That means I could treat one of these lines like it's the base, and one line like it's the height, and I can use 1/2 base height. So we need to find the lengths of AC and BC. And we know how to find the lengths of line segments. If we know coordinates, we're going to use the distance formula. I'm going to just write out that formula once here. x2 minus x1 squared plus y2 minus y1 squared, all under a square root. So for AC, let's see, C is 5, 5, so we've got 5 minus 3 squared plus, or that's, I guess I started with y2 minus y1, but that's fine. And then 5 minus a negative 5, so 5 plus 5 squared. So we've got 2 squared plus 10 squared. We have the square root of 104. And you could approximate this. I'm going to go ahead and just simplify the radical. So maybe we're doing a little bit of review here. If you don't quite remember how to simplify a radical, or can't, maybe it's been a little while since you've done it, what we're going to do is just factor the number 104. And there's, let's see, we could take out a 2, and then we get 52. We can take out a 2 and get 26, and then we have 2 and 13. So we look for pairs of the same factor. I've got a pair of 2's here, so I could take out a 2, and what's left inside, there's no more pairs, so what's left inside is 2 times 13, or 26. So 2 times the square root of 26. There's the distance of the line segment AC. Now for BC, I'm going to do the same thing. Let's see, x2 minus x1 is 5 minus 6 squared plus y2 minus y1 is 5 minus 0 squared. So I get negative 1 squared plus 5 squared, and that gives us 26. So I have the square root of 26. And now I have my base and height for this triangle, and I can finish 1/2 times base height is 1/2 times 2 root 26 times root 26. Now this simplifies really nicely. 1/2 and 2 cancel. Root 26 times root 26 is 26.